So for this session, we'll be talking about fundamental theorem of calculus. And this beautiful theorem here, it relates the antiderivative that we have just discussed and the definite integral. Okay? So let's start with the first part of the theorem. So we call this the fundamental theorem of calculus 1. Okay? By the way, this numbering here, we have two parts. Fundamental theorem calculus 1, fundamental theorem calculus 2. In other references, okay, they are reversed. In other references, this is the fundamental theorem of calculus 2, okay? And my fundamental theorem of calculus 2 is the fundamental theorem of calculus 1, okay? And of course, there are references where this is the FTOC 1. But anyway, if f is continuous on, or if small f is continuous on the closed interval AB, then the function capital F defined by this, okay? So capital F of x equals the definite integral of f of t dt from a to x, okay? Where x is between a and b, inclusive. So this function here, it is continuous on the closed interval AB. It is differentiable on the open interval AB. And furthermore, if you get the derivative of this capital F of x, this will become small f of x. Okay? Now, because of this condition here, it means that this capital F of x is actually an antiderivative of small f. Okay? So we will see that later. Now, things that we need to emphasize here, your small f of x must be continuous on the interval AB. If your small f of x is not continuous, then this may be false. Okay? So if f is not continuous on AB, then this may be false. We don't know what the conclusion is. But if f is continuous, this small f here is continuous on AB, then we are sure that this capital F of x here, it's continuous on AB, and it's also differentiable on AB. That's one. Second, here, this is your x. The x is an upper limit of integration. Okay? This is your x, that's the x there. So the function capital F, it's a function of x. This x here, it's the upper limit here. Okay? And then the lower limit, this is just constant. Okay? It's fixed. In this case, it's actually the leftmost endpoint of your interval. Take note, your x will only take values from A up to B, inclusive. So the lower limit of integration here, it is this leftmost endpoint of your interval. And of course, inside here, okay, t and t here, these are dummy variables. You can replace them with other variables, but not x. So you can replace this with s or z or y, any other variable except for x. Okay? If you have a variable as a limit of integration here, either here or here, the variable here should not be x. it should not be the same as the one or as the variables you put as limits of integration. Okay? So again, small f continuous on the interval, the closed interval AB. Capital F, it's a function of x. This x here, it's an upper limit of integration, and the lower limit of integration must be constant. So that when you have this, if you get the derivative of capital F, it will become small f of x. Okay? So here are some remarks. I think I mentioned some of these. So it follows that the function capital F, this guy here, is an antiderivative of small f. Now, if small f is continuous on AB, then we can write this fundamental theorem of calculus 1 as this small f of x, it's equal to the derivative with respect to x of the definite integral from a to x of f of t dt. And I want to put into quotation marks this definite integral. So this guy here, it looks like a definite integral. But then again, the upper limit of integration here, it's a variable. For the definite integral that we've learned, both lower and upper limits of integration, they are fixed number. But for this, x is changing. Okay? Question? So what does this mean? It's like the integral is being cancelled by the derivative. Correct? It's like the integral is being cancelled by the derivative. You have integral here of some function, but you get the derivative, so they are just being cancelled. Okay? But again, keep in mind, the upper limit of integration, it's x. The lower limit of integration, it's a constant. And x is your variable. And the t here, these are dummy variables. You can replace them with other variables except for your x. Okay? Examples. We have this. We have the function g here. So let's look at number 1. This is your function g, and we want to get the derivative of g. Your g of x, it's equal to the integral from 0 to x of square root of 1 plus t cubed dt. So this is straightforward. G prime of t, this is just the derivative with respect, sorry, g prime of x, not g prime of t. G prime of x, it's the derivative with respect to x of the integral from 0 to x square root of 1 plus t cubed dt, and this is simply square root of 1 plus x cubed. That's it. You'll just replace this t here with that x. That's what happened here. Capital F of x, you have here, and then this is f of t. If you get the derivative of that, you'll just replace this t here with the x. So that's what we did here. So whatever is in here, you'll just use that as a replacement for whatever inside here. Okay? Question? Number 2, we want to get the derivative with respect to x of the integral negative pi over 4 up to x cubed of tangent t dt. By the way, in here we did not check if the function is continuous, but as you can see, although you have a square root here, actually you have a square root here, and then you have 1 plus t cubed here. Okay? The value of t, so that this square root here is defined, okay, must be t greater than or equal to negative 1. Okay? T must be greater than or equal to negative 1. So if I'm going to add that, t greater than or equal to negative 1. If t equals negative 1 cubed, that's negative 1. 1 plus negative 1, that's just 0. So this is still well defined. And of course, if t is greater than negative 1, t cubed will also be greater than negative 1. Which means that 1 plus something that is greater than negative 1, this becomes a positive number. So this will be continuous for t greater than or equal to negative 1. Now in here, tangent t, this is continuous at every real number except at pi over 2, 3 pi over 2, or odd pi over 2. So in here, we can have what? The t here, it can be inside negative pi over 2 up to pi over 2. So what does that mean? You need your x cubed here to be inside this interval also. In here, by the way, your x must also be greater than or equal to negative 1. So that your definite integral is defined, okay? And we will not have any problem. Okay? So anyway, t inside negative pi over 2 to pi over 2, this tangent t is continuous. So we can use that. Okay? So we will assume that we are inside the interval for which this is continuous. Okay? So what is now the derivative of this function here? This will be what? So what you're going to do, you replace the t by the one here. Okay? So this becomes tangent of x cubed. Okay? But this is x cubed. Okay? In our theorem, we should only have x. So what we're going to do is to apply chain rule. Okay? Since this is x cubed. So by chain rule, we have to multiply this by the derivative of x cubed, which is 3x squared. Follow? Any questions? Lastly, we have this y here. It's the integral from sine x to 1 of square root of 1 plus s squared ds. Now look at this. The upper limit of integration, it's just 1. The lower limit of integration, it's sine x. But according to this, the x must be the upper limit of integration. the constant, the fixed number must be the lower limit of integration. Therefore, we have to interchange the two. And remember, when you interchange that, when you interchange this, you have to put out a negative. Okay? So this is the negative. We are now ready to interchange those limits of integration. And then here you have 1 plus s squared ds. But that's just your y. We want y prime. So we do similar thing as this. We have here y prime equals. Don't forget the negative. So you have negative. And then you copy the function and replace the dummy variable there by the one in the upper limit of integration here. So you have square root of 1 plus sine squared x. And then by chain rule, we want to get the derivative of this sine x, and that's cosine x. So this is the final answer to that. Okay? Question in the fundamental theorem of calculus 1. Okay? Now let's go to the fundamental theorem of calculus 2. If small f is continuous on the closed interval AB, and capital F is any antiderivative of small f on AB, meaning the derivative of capital F, that's just small f, then this guy here, the definite integral of f of x dx from a to b, this is just capital F of b minus capital F of a. Okay? So this theorem helps us solve definite integral without using the definition. So in the last lecture, when we solve definite integral, we use definition, we use limit of Riemann sums, or maybe we can use the area. This time, this theorem helps us solve this definite integral by searching for antiderivative. And then we just evaluate. Okay? You may take any antiderivative. Okay? Take note of that. Any antiderivative. So you can take any antiderivative of small f. Okay? Why? For example, suppose you have an antiderivative capital F, and then you put the arbitrary constant c. Then this guy here, capital F of x plus c, it's also an antiderivative of f. Okay? So if we apply this, if we apply similar to this, you have here, this is your antiderivative now. Okay, take note of that. So if you evaluate this at b, you will have capital F of b plus c. That's constant. It will not change. Minus. So that's your minus. And then if you evaluate this function here at a, you have capital F of a plus, again, c. It's just c. And therefore, you will see, you will see this c minus c. So they will just cancel out. And eventually, you'll be left with capital F of b minus capital F of a. Okay? Questions? Now, I would like to introduce this guy here. Another notation here is just, you can write this as capital F of x evaluated. X equals A, x equals B. Or you can even remove this x equals. You can just write evaluated from A to B. Okay? So every time you see that, say capital F of x evaluated from A to B, this means capital F of B minus capital F of A. Okay? And take note again, before using this theorem, your function small f must be continuous. Okay? Question? Now, earlier I said that the integral, okay, that in here, it seems that the integral is being cancelled by the derivative. Okay, so it seems that the integral is being cancelled by the derivative. For the second fundamental theorem of calculus in here, take note, small f of x, that's capital F prime of x. So if you do that in here, okay, if you do that in here, so you have integral f of x from a to b dx. This is what? Integral from a to b of capital F prime of x dx. And according to the fundamental theorem there, this is just f of b minus f of a. Correct? And if we use this notation, you have here capital F of x evaluated from A to B. Notice, inside the integral symbol, you have a derivative. So in here, it's like you get first the derivative and then you integrate it. And you will get your function back. So this guy here, it seems that the derivative is being cancelled by the integral. Okay? So, combining these two guys, fundamental theorem of calculus 1 and fundamental theorem of calculus 2, as a whole, it's the fundamental theorem of calculus. It actually tells us that the integral and the derivative cancels each other. Okay? One cancels what the other does. The integral cancels the derivative cancels the integral. Okay? Any questions? Now, our main goal, let's solve definite integrals. So we want to evaluate the integral e to the x dx from 1 to 4. We need to find antiderivative for e to the x. So you have your f of x here. This is your e to the x. Okay? An antiderivative we can use capital F of x equals e to the x. And indeed, if you get the derivative of this capital F of x, you will get your small f of x here. The derivative of e to the x is itself. Therefore, we have the integral from 1 up to 4 of e to the x dx. This is simply e to the x evaluated at 1 and at 4. And this one here equals e to the 4 minus e to the 1. So this is the answer to that definite integral. Okay? Questions? Next, find the area under the curve of y equals x squared over the interval -2 to 1. Area under the curve. Okay? You have here the function y equals x squared. So over the interval -2 to 1, so you will have something like this. Okay? So this is 1, and then this is -2. So the area under the curve, the region is here. So you want to find the area under the curve. Area of the region under the curve, to be more precise. So this is your y equals x squared. But we've learned this area is just integral. And since, as you can see, both regions are above the x-axis, okay? This region here, it's above the x-axis. This region here, it's above the x-axis. Then the area is simply, okay? Then the area, it's simply the integral from -2 to 1 of x squared dx. Okay? Now, if f of x is x squared, then capital F of x, which is x cubed over 3, is an antiderivative. Is an antiderivative of small f. Of small f. Correct? If you don't believe me, just get the derivative of capital F. And you should get this small f of x. And therefore, by the fundamental theorem of calculus, this guy here, it's simply x cubed over 3 evaluated -2 up to 1. So this guy here, at 1, you have 1 cubed over 3 minus at -2, this is -2 cubed over 3. So if we simplify this, we have 1/3 -2 cubed, that's -8. And then we have minus here, so we have plus 8 over 3, and this is 9 over 3. And therefore, this is 3 units. So the area is 3 units. Okay? Oops. Questions? So For my next examples here, the solutions will be similar to those that we have done. So this guy here and um, this guy here, very much similar. And also, yeah, those two examples. So from this point on, I will not put this on record. So try to work on them if you are rewatching right now. So we have this function, we have this example, and then this example. Okay?